Welcome to the multivariable calculus section. In this section we'll be discussing triple integrals in cylindrical coordinates. So previously we learned double integrals in polar coordinates where x is equal to r cosine theta and y is equal to r sine theta. But triple integrals, we know, incorporate the third component, which is the z component. So what would z equal in terms of cylindrical coordinates? Well, it's very, very interesting to understand that z is actually equal to itself. So when substituting for z, z is just equal to z. So that makes that very simplistic. But when we're dealing with dv, we also know that there's an additional component. So it's no longer r dr d theta. Well, it's very interesting to note again, all that we add is a dz. So it's just dv is equal to r dz dr d theta. It's not too different, right? And from our D, our domain, our general region, we said r cosine theta, r sine theta, etc., and these are just our bounds, but all we're doing here is saying that r cosine theta, r sine theta, z, alpha less than theta less than beta, h2 theta less than r less than h1 theta, and the u1 of our cosine theta, r sine theta, which is just essentially saying that u is a function, or our z function, and we're saying is less than z, and etc. It's the same thing except with a u2. And that would just be our general region. So that means our triple integral in cylindrical coordinates is going to look like the following. So this is our Cartesian, the general region, x, y, z, dv is just equal to beta alpha, h2 theta, h1 theta, u2, u1. And that is of fr cosine theta, r sine theta, z, r dz dr d theta. And as you can see, all we're doing is adding an integral, an integration component, which would be our z component, and incorporating a new substitution. But essentially it's not a substitution because it's just itself. So I hope that helps. If you need additional assistance or more problems to do, there's a bunch on the website. Thank you.